right, so let's get cracking.
Yep.
Hello, everybody. Hope that you're all well. On Tuesday evening, we were talking about solving cubic equations. And what I wanted to do was relate that to what we're doing tonight when we're talking about the sketching of the cubic function, because we need to be able to solve cubic equations if we want to sketch functions. Because when we're solving a cubic function, in essence, what we're doing is we're making y equal to 0 and we're solving for x. What do you think that means we're calculating? If y is 0 and we're solving for x, what are you calculating when you solve the cubic equation?
The x-intercepts.
Exactly, the x-intercepts. Okay, so we've got to show the x-intercepts of our function because we always show the x-intercepts and the y-intercepts of any particular function. Okay, so when you're solving a cubic equation, you're actually solving the x-intercepts. Okay, so if we have a look at this first one over here, making y equal to 0, it's nice and easy. Every single term has an x in it. So what can we do to this particular equation? If every single term has an x in it, we can do what? Take an x out. Exactly, Natalie. Okay, so we're going to take x out as the highest common factor. That leaves us with x squared minus 12x plus 36. And once we've done that, we can factorize the resulting trinomial. In this case, it would look like this. All right, and now the question is, how many distinct solutions for x will I have? How many distinct solutions for x do I have in this case? Good, Natalie, well done. I have 2. So either x is 0 or x is 6. Okay, so when this bracket doubles up, so I've got an x minus 6 times an x minus 6, it means something very specific. Okay, but I'm not going to talk about what it means now. Thanks, Jerry. It means something very specific, but I'm not going to talk about what that means right now. Okay, well done. Perfect. So I've got 2 solutions. Let's consider this one over here, right? Again, we're going to solve for x. So the first thing that I need to do is get all the terms over to one side. So I've got x cubed minus 12x plus 16 equals 0. Okay, I can't take an x out, right? So what do I have to do, Matrix? Exactly. Okay. Pinga, log out and log back in again. Just, Yolanda, just tell Pinga to log out and log back in again. Exactly. It's a cubic polynomial. It's a cubic equation.
I'll handle that.
Thank you so much. And like Natalie said, I need to find a factor. So I want you guys to sub in, use factor theorem, as we've discussed, and tell me what the linear polynomial is, or what a linear polynomial is, because it obviously be more than one. So for this particular equation, I want you guys to give me the linear polynomial, a linear polynomial that I can use. Okay, so Natalie says the first bracket is x minus 2. So Natalie, you've discovered obviously that f of 2 equals 0. So that means that x minus 2 is a factor. Okay, so I've got x minus 2. And now here I've got ax squared plus bx plus c equals 0. Can you guys work out the values of a, b, and c and tell me what they are? Okay, so this is putting into practice what we learned last time. Can you tell me what a, b, and c are equal to? Okay, so I want the values of A, B, and C from you guys, please. Good. A is 1. Well done, Natalie. C is -8. I quite agree. Okay, so we just got to work out the value of B. Good, Seppo. Okay. Nizoli, B is 2, not 10. Okay, so just be careful. A is 1. So Nizoli, when you go to work out your bx squared term, you've got bx squared minus 2 times 1x squared. So that's minus 2x squared. And then remember, because there isn't an x squared term in here, you would make it equal to 0x squared. So b minus 2 would be equal to 0. So that means that b is equal to 2. Okay, so you've got x minus 2 times 1x squared plus 2x minus 8. Okay, matrix, factorize the trinomial. What would we get? So you're going to factorize the trinomial. What factors do you get, matrix? Zedalia says, okay, Zedalia, it's just your signs that are incorrect, my girl. It should be x plus 4 times x minus 2. Just careful of your signs, but well done. Okay, so again, how many distinct solutions do I have? Good, well done. That's it, in so quite right. Okay, so the middle term is positive, the last term is negative, so the bigger of the two factors must be the positive one. Okay, no problem. All right, so two distinct solutions, either x is 2 or x is equal to -4. All right, good stuff, everybody. I'm glad we all know how to solve a cubic equation now. Let's go forward and go and talk about what's going to happen with the graphs. Okay, so all cubic functions have the same general equation. That is f of x or y equals ax cubed plus bx squared plus cx plus d. All right, a cannot be 0. All right, so a can be a negative number or it can be a positive number, but it cannot be equal to 0 for a cubic function. We'll talk a little bit more about what a means for our cubic function now. B can be 0, C can be 0, D can be 0, but a can't be 0. D is a constant. Okay, so it is a constant. It means it's a number on its own, and that is your y-intercept. Okay, so it's always your y-intercept. Now, as far as A is concerned, all right, when you have a parabola, so f of x equals ax squared plus bx plus c, A also affects the shape of your parabola. So if A is positive in your parabola, what shape parabola have you got? Exactly, you got a happy face, a smiley face. So your parabola looks like that. On your parabola, if A is negative, then you've got a that's it, got a sad face. Okay. All right. So when we get to matric, we learn names for this. Okay. So they never talk about it before matric. They don't talk about concavity before then. All right. But they talk about it now that we get to matric. So when our graph is smiley face, we would refer to this. Let me just scooch over to the side a little bit. We would refer to this formally as concave up. That's it. Good. Well done. When it's sad face, we would refer to this formally as concave down. Okay, so concave up and concave down. Good, well done. So let's go back to our cubic function. All right, so on the left-hand side, A is positive. Okay, so we're looking at this one over here. A is positive. Right, so your cubic function is shaped like this. First, it is concave down. It's first concave down, and thereafter, it is concave up. Okay, so that's something that you guys have to learn. Okay, it's concave down, and then it becomes concave up. All right. Then if A, let's choose a different color here. If A is negative, your graph is first concave up, and then, let's just get the purple again, it's concave down. Okay, and that will be the same for all cubic functions. All right, so the sign of A is very important in helping us determine the shape of our cubic function. Okay, so if A is negative, it's first concave up, and then your graph is concave down. Okay, now, somebody asked me to unmute them. Hang on a second. If you wanted to ask a question. Mogetswalani. Maybe you can help, Yolanda. I got a direct message.
Oh, it's a direct message. That's why I didn't see it on the chat.
You know,
Sorry.
you wouldn't. You wouldn't.
They can unmute themselves. They just have to press. So if you can hear us, you just have to go where it says mute and you need to press there and then you can be able to talk. But of course you need to raise your you have to choose the reaction button and then you click on the raise on your hand like that, and then Teacher Lee will tell you to talk because we can't have everybody unmuting themselves, but you have the right to unmute yourself. We don't have to unmute you. Yeah.
So if you do want to ask a question, you're welcome to put your hand up. Otherwise, I'm going to continue on. So let's barrel on and let's talk about some important points, okay? So here is a cubic function where A, oh, beg your pardon, it's the wrong way around, where A would be a positive. Okay, it's concave down and then concave up. So it's characterized by the following, okay? We have two turning points. So the turning point that is in yellow, all right, that's a turning point. And that would be referred to as our local maximum. The turning point in pink would be referred to as our local minimum. Okay. At both of our turning points, our gradient would be 0. Okay. So at the turning points, the gradient is 0 and the graph changes direction. To the left of the yellow turning point, all right, is the graph increasing or decreasing? To the left of the yellow turning point, is the graph increasing or decreasing, Matrix? Okay, so to the left of the yellow, right? So in other words, if I was standing over here and I'm walking in that direction towards my turning point, I'm walking uphill, walking uphill. So that means that the gradient is increasing. Okay, so when I get to the top of the hill, the gradient is 0. between the turning points. So once I get to the turning point, I'm not going up, I'm not going down. So now when I'm in between my turning points, now my gradient is decreasing. Okay, then I would get to my pink turning point and my graph changes direction again. And now I begin walking uphill. So now again, I am increasing. Okay, so the gradient changes depending where on the function you are. Okay, so it increases initially if a is 0 to your local maximum where gradient is 0. Then your graph changes direction. Your gradient is decreasing to your next turning point, your local minimum. And then it changes again and it becomes increasing. Okay, so we use symbols for the words increasing and decreasing. Okay, so just quickly here on the side, when I refer to y, I call y f of x. What symbol do I use for gradient? Okay, m. But in terms of f of x, what would I use? What symbol do I use for gradient? The derivative, the first derivative, that's it, Katlego. Okay, so I would refer to gradient as f prime x. Okay, so this is gradient. Okay, so f prime x is the symbol for gradient when we are talking about functions. Okay, so another way of me saying that the graph is increasing is for me to say that f prime x is greater than 0. Okay, the gradient is positive. Another way for me to say that the gradient is decreasing is to say f prime x is smaller than 0. Okay, so another way for me to say that the gradient is increasing is to say that f prime x is greater than 0. Okay, so it's very important that we know these symbols. All right, so it's not just the gradient that changes depending where on the function we are. We've also spoken about concavity and that the graph changes from being concave up to being, concave down to being concave up, right? Now, the point at which this happens, where the concavity changes, it has a specific name. Does anybody know what that name is? Where does the concavity change? Yes, with your second derivative, but what's the point called on the function? Nicole?
Point of inflection.
That's it. So it's called our point of inflection. Okay, and that is the point at which the graph changes from being concave up to concave down or concave down to being concave up. Okay, so this is where we have a change in concavity. Okay, so we have a change in gradient at our turning points, and we have a change in concavity at our point of inflection, right? What is the symbol for concavity? What's the symbol for concavity? That's it, Nkani. So our second derivative. Okay, so our second derivative is concavity. Our first derivative is gradient. Okay, so very important that we learn the difference between those two. Okay, so we would say that at the point of inflection, your second derivative will be equal to 0. At the turning points, okay, your first derivative is equal to 0. Okay, so I'm going to say that again. At your turning points, your first derivative is equal to 0. At the point of inflection, your second derivative is equal to 0. Okay, your first derivative is gradient. Your second derivative is concavity. Okay, any questions on these particular function or particular features of our cubic function? Katleho.
Ma'am, what is the use of the point of inflection, ma'am? Because I do not understand it that well, ma'am. I don't get it because I do know that it's used while drawing the graph, but I don't know how to use it.
Okay, so where they would expect you to use it, Katleho, is they would ask you a question like this: for which values of x is the graph concave down? Or for which values of x is the graph concave up? Okay, so you're going to use the second derivative to describe the concavity of the graph. All right, but I'm going to show you that in questions that we're going to do, maybe not this lesson, but in lessons that will come. Okay, so you don't actually need the point of inflection to draw the graph. Right, it's not actually one of the points that we would show when we were just asked to sketch the function. Okay, so it would be in an analysis type question where we would want to know the x coordinate at the point of inflection. Okay, all right. So now that we've discussed the features of these functions, oh, by the way, everything is reversed for a graph that is shaped like this. Okay, so first this graph would be decreasing, then increasing, then decreasing. All right, so a graph where A is negative is going to be increasing between its turning points. Okay, a graph where A is positive will be decreasing between its turning points. All right, so here again, there is your local minimum where your gradient is 0. Here's your local maximum. Okay, where again, your gradient would be equal to 0. Okay, so this would be decreasing, increasing, decreasing. Okay, so just the other way around. All right, also as far as concavity is concerned, this graph is first concave up. So concave, oopsie, that's badly drawn. So first concave up, and then it would be concave down. Okay, whereas your graph where A is positive is first going to be concave down. So that would be this bit up to your point of inflection, concave down first, and then it would be concave up. Whoopsie. Okay. All right, so now that we know what these graphs look like and what their important features are, let's go and talk about how we would sketch them. So take screenshots at this stage. This is an important piece of information, and it's going to help you be able to sketch a cubic function. All right, so first things first, our intercepts with our axes. So we've been sketching functions for a long time, since grade 10. The rules haven't changed when it comes to the x and y intercepts. For the y-intercept, we let x be 0 and we solve for y. For the x-intercepts, we let y be 0 and we solve for x. That is easy enough. Okay, so for example, here we have this particular function. I'm just going to move, sorry, I changed this later on. We're going to go back to this same function that we were speaking about earlier. Okay, so if you recall at the beginning of this lesson, we solved this particular equation, right? If you remember over here, there it was. We solved this. Okay, so let me just cut this out and pop it there for us. Just make life easier than writing it all over again. Okay, so here we made y equal to 0. We solved for x. So this was us solving our x-intercepts. Okay. this equation is in the form f of x equals ax cubed plus bx squared plus cx plus d. Okay, can you see that the constant d is equal to 0? So that means as far as your y-intercept is concerned, y would be equal to 0. So this graph goes through the origin. Also, you can see here one of its x-coordinates is 0, so it goes through the origin. All right, whilst the other x-intercept is at 6. Okay, so that's how we would calculate the x-intercepts and the y-intercept. Okay, that's something that we've been doing for a long time. Now let's talk about how we would calculate the coordinates at the turning points. Okay, so recall, at your turning points, your gradient is equal to 0. F prime x is 0 at the turning point. So that's what we have to do. We have to take the first derivative and we have to equate it to 0 and solve for x. Okay, so this is what we would do. There's our equation. So f prime x, using our power rule, we would end up with 3x squared minus 24x plus 36. We have to show that the gradient at the turning points is 0. So you must write that 0 over there. So we'd end up with 3x squared minus 24x plus 36. Each of these is divisible by 3. So that means that we would end up with x squared minus 8x plus 12. Now it's going to factorize. Okay, so we are going to end up with x minus 6 times x minus 2. Right, so that means that at our turning point, x is equal to 2 or x is equal to 6. We also need the y-coordinates at our turning points. So in order to get the y-coordinates at the turning points, we sub the x values back into the original equation. Okay, so once we have our x-coordinates, for the y-coordinates at our TPs, we're going to sub x back into the original equation. Okay, and that's because the points lie on the original graph. Okay, so what we are now calculating essentially is f of 2 and f of 6. Okay, so I'm going to calculate f of 2 first. So subbing 2 in, I'd get 2 cubed minus 12 times 2 squared plus 36 times 2. Okay, so what would that give me? What are you guys getting as an answer? Me too, I'm also getting 32. Do we already know what 6 gives us when we sub it back in? Do we know what f of 6 is? Yes, it's 0. Good, well done, Natalie. Okay, so there's no point in us doing this because we actually already know what the answer is. We know that it's 0. Okay, so that comes from our x-intercept because our x-intercept is also a turning point, or one of our x-intercepts is also a turning point. So as far as our turning points are concerned, we've got 2 and 32 and 0 and 6. Okay, so just going back to this, we've determined f prime x, we've equated it to 0, we've solved for x. We then substituted our x values back into the original equation to obtain the corresponding y values. Okay, if the function has two stationary points, establish whether they are maximum or minimum turning points by referring to the shape. Okay, so what shape is this particular function? What shape does it have? So we're referring to the concavity now. What shape is this function, matrix? Okay, A is positive, Natalie, but it's shape. So talk about concavity. Okay, so if A is positive, let's go back up here again. If A is positive, it looks like the graph on the left. First, it is concave down. Then it is concave up. Okay, so that's what I mean when I'm talking about the shape. Okay, it's first concave down and then concave up. All right, so this particular graph, whatever it looks like, it's going to do this. Okay, it's first concave down and then it's concave up. Okay, you see what I mean now? All right. So if we now have to decide what these points are, whether they are maxima or minima or local maximums or local minimums, we've got 2 and 32 and we've got 0 and 6. Okay, so 0 and 6, let's do that one first, is going to be a maximum or a minimum. 0 and 6 is going to be a maximum or a minimum. Good. Good. I'm glad it makes sense, Nolitando. 0 and 6, is it a maximum, a local maximum or a local minimum, matrix? Nope. Okay. So this point over here has to have a smaller x than this one over here, doesn't it? Oh, sorry, guys. Sorry, it doesn't change anything. Beg your pardon. Sorry, matrix. Yes. Sorry, x is 6 and y is 0. Okay. All right. So, okay, that's right. So then this would be the minimum. Yes. So this would be the local minimum. That would be over there. And 2 and 32, that would be our local maximum. Okay, so that would be the point that would be over here. So this one must have a smaller x value than that one over there. Okay. No. Sorry, Natalie. No, you're quite right. Sorry, I don't know why I swapped those around. It obviously doesn't help if one does that. Okay, but you're right. It was 6 and 0. Okay. Are we all good so far? Is everybody happy? Is this making sense to everybody? Are we thumbs up? Just checking in with you. Cool. All right. Cool, Keithlin. Thanks, and Kanyisa. Good, Miss Cindy. All right. Okay, so how far are we? Okay, so we have found the coordinates at the stationary points or turning points. Good, Nicole. Good, Katlejo. All right, so we are okay with that. Right. Now, as far as the point of inflection is concerned, right, you do not need to show the point of inflection when you sketch a cubic function. If they ask you to show it, then do, but otherwise it's just the intercepts with axes and the coordinates at the turning point. Okay, so as far as your point of inflection is concerned, that is where your concavity changes. All right, so let's just talk about how we would find the coordinates at your point of inflection. So there are 2 ways in which you can do this. Okay, the first way is to use your second derivative. At your point of inflection, your second derivative is equal to 0. Good, Natalie. Yes, 100%. So you're going to derive the first derivative. So your second derivative, in this case, would be equal to 6x minus 24. At the point of inflection, concavity is 0, so you'd make that equal to 0. So that means that 6x would be equal to 24, so x would be equal to 4. That's the x coordinate at the point of inflection. Good, yes, I agree. The other way that you can do this is to use midpoint formula. And that is because your point of inflection is always halfway in between your turning points. Okay, so your point of inflection is always midway between your turning points. Okay, so the x coordinate at the point of inflection, sorry, and this doesn't help because I wrote that the wrong way around as well. Let's just quickly change that. That was 6 and 0. Remember, these were the coordinates at our turning points. Okay, so we would say 2 plus 6 divided by 2. So that gives us 8 over 2. Can you see we get the same answer of 4? Okay. It is, isn't it? It is. Okay, so there are two ways to calculate the coordinate or the x coordinate at your point of inflection. Either you can use the second derivative or you can use midpoint formula. All right, so both are perfectly acceptable. All right, the y coordinate at the point of inflection never gets asked. It has no relevance for us here. Okay, so they probably will not ask you to do that, but if they did, you'd sub 4 back into the original. Okay, all right, so now that we've got all this information, let's put it together. Okay, so we've got a y-intercept at the origin at 0. We've got an x-intercept at 0 and at 6. We've got turning points at 2 and 32 and 6 and 0. Now we need to draw the graph. So remember, okay, we had already decided that A was positive and our graph had to be shaped like that. Okay, so let's give ourselves an x-axis. All right, so we know that the graph has an x-intercept that's also a turning point that is at 6. So that point over there has to be 6 and 0. This point over here is the point 2 and 32, which we know is in the first quadrant. All right. The graph has another x-intercept at the origin and its y-intercept at the origin. So that means that that point over there, oopsie, has to go through over there. So that would be 0 and 0. Okay, that's what your graph would look like. Exactly. Okay, so you are going to get marked as follows. You are going to get marked when you've actually sketched the function, you're going to get marked on shape. Okay, so that means concave down, then concave up. You are going to get marked at the coordinates of your turning points, and you are going to get marked for your x and y intercepts. Okay, so those are the 3 places where marks are awarded. Any questions? Oh, you're all good. Okay, Keithlin's giving us a thumbs up. How's everybody else feeling? Is it making sense? Cool, Nicole. Natalie's good. Sepo's happy. Sebusiswe is happy. Good. Eve, you're smiling. That's nice. Miss Cindy's happy. Yes, Tsehufatso, paper 1. Okay, so Katleho, you're asking where does 0 and 0 come from? Over here. Okay, remember, Your y-intercept was at 0. And you've got an x-intercept over here, so that would also be 0 and 0. Okay. All right, good. All right, good stuff. Yes. So, Abulele, you take the first derivative and you derive it again. Okay. So if you have a look, your first derivative was 3x squared minus 24x plus 36. Your second derivative is 6x minus 24. Okay. Katleho, all this kind of working out, these will be questions that they will get you to do before they ask you to sketch. All right. So as far as solving the x-intercepts are concerned, there would be a mark for equating it to 0, a mark on your factors, and a mark on your answer. So that's out of 3. As far as the coordinates at the turning point are concerned, there's a mark for the first derivative, a mark for making it equal to 0. Sometimes they give you a mark on this line over here for your factors, and then they can give you a mark on your answer, and then a continuous accuracy mark here on your y's. Okay, so that could be out of 5. Okay, often is. As far as your point of inflection is concerned, all right, so there would be a mark for the second derivative, making it equal to 0 and your answer. Here, they would also have to give you 3 marks. So midpoint formula, I'm not sure where they would fit the extra mark in. I don't know. They would obviously have to put a 3rd mark in here, but I'm not 100% sure what they would make that for if they did it this way. Okay. Maybe they wouldn't give you a mark here. Maybe they'd make it out of 2 and they wouldn't give you a mark for the 0. Okay. Maybe, in fact, actually, I think that's what we would do. I don't know why it's taking me. So 1 mark, I think, for the second derivative and equal to 0. Okay, so just 2 marks for that. That wouldn't be out of 3. Okay, so you can see how many marks. So 3 and then 5. And then they could say, hence, sketch the graph of f of x. Okay, showing all intercepts with axes and the coordinates at your turning points. All right. Okay, we don't have a lot of time left. I don't know if we will manage to do this, but perhaps I can get you started and you guys can do the rest for homework. All right. This graph over here has a equal to -1. Okay, so a is negative. All right. Let's do the y-intercept first. What would the y-intercept be for this particular function? That's it. Okay, so the coordinates at the y-intercept would be 0 and -8. All right, what would we do for the x-intercepts? What would we do for the x-intercepts? Exactly, we would make y equal to 0. So we'd have 0 equals -x cubed plus 2x squared plus 4x minus 8. And then what would you do after this, do you think, if you've got the negative there? Okay, before you find your factors, there's something that you can do just to make life a little bit easier for you. Exactly. Get rid of the negative. Divide through with -1. Well done. So you'd have positive x cubed minus 2x squared minus 4x plus 8. Now use factor theorem to find your linear factor. Okay, so someone give me a linear factor, please. Nicole?
The factor is x plus 2.
Is x plus 2. So in other words, f of -2 gave you 0, so x plus 2 is a factor. Okay. All right. So that gives us, okay, so now we need to work out the values of a and b and c again. You see, this is why we need to be able to solve cubics. Okay. All right, Nicole, you are saying x minus 2. Okay. So just be careful here. Maybe it's both. Works both ways. All right. Okay, so +2 gave you 0 and -2 gave you 0. Just be careful. Are you guys using this equation over here? Is it going to make any difference? It shouldn't. Natalie.
Yes, ma'am. It works for both of them. I just tested
It works.
with
You just
two
tested it
and
works for both of them. Okay.
Yes.
All right. So do you want -2 or +2? Which one do you want me to use?
Anyone is fine, ma'am. Anyone
You
is fine.
pick.
Okay,
You
let me
pick.
say x minus 2, ma'am.
All right, that's fine. Okay, so Natalie has selected -2. Cool. Let's find the values of A and B and C, please. So Natalie's chosen x minus 2. Let's find the values of A, B, and C. Values of A, B, and C, please, matrix. Good, not a tunder. A is 1, I quite agree. C is 4. Good. Nice. Oh, but hang on a second. If we're doing what we're doing here on the screen, then it would be equal to -4, wouldn't it? -4, yes. Okay, what's B equal to? Okay, so we're getting different answers. Sepo is getting 0. Shania is getting -4. Let's just double check. So we would end up with bx squared. Then we've got -2x squared. And then that would be equal to -2x squared. Okay, so b minus 2 equals -2. So b would be equal to 0. Okay. All right, remember we're using this one here because we divided through by -1. Okay, it's no, Latunda, that's fine. That's fine. Then yours would be a little bit different. Okay, not a problem at all. Okay, I just didn't want us all to be doing that. Doesn't matter. So here we end up with x squared minus 4. Okay, so that's difference of 2 squares. That's not a trinomial. So this would be x minus 2, x plus 2 times x minus 2. Okay, so we've got 2 distinct solutions in this case. Either x would be equal to 2 or x would be equal to -2. All right. So when we see a bracket being multiplied by itself, that means that at that value of 2, it is an x-intercept and a turning point. Okay, we saw the same thing when x was equal to 6 in the previous example. Okay. So x minus 2, where x is equal to 2, that's going to be an x-intercept and a turning point. Lovely. Okay, so we've got the y-intercept, we've got the x-intercepts. Now we want the coordinates at the turning points. Okay, so guys, f prime x. Now we're going to go back to the original equation. Okay, that's going to give us negative 3x squared plus 4x plus 4. Make it equal to 0. Divide by negative 1 just to make life easier for you when you factorize. Okay, Shania. And factorize. Okay. Is this going to factorize? Yes, it will. Okay, so that gives us minus 6x plus 2x, and there we go. All right, so therefore, x is equal to negative 2 over 3, or x is equal to 2. Okay, do you see what I mean when I said when the bracket doubles up like that? Okay, that value of x is going to be an x-intercept, and you can see here it is a turning point as well. Okay, so you know that one turning point is at 2 and 0. Now you need to take this and go and sub it back into your original equation. Okay, so you need to calculate f of minus 2 over 3 using your original. Okay, so our original was this one over here. And we're going to get a fairly nasty y coordinate, but that's okay. That happens sometimes when a nasty fraction goes in. And I think this is all we're going to have time for. We might just be able to draw the graph. Yeah, what is it, Natalie? It must be nasty.
Oh, ma'am, it's the worst. I got negative 256 over 27. So I got negative 256/27. Yes.
Okay. All right. Lovely. Okay. So now that can happen. That's perfectly normal if you have now gone and subbed in a nasty fraction going in. Okay. You're going to end up with a weird answer like that. Okay. So what this means is that, sorry, Yolanda, I know you want them to do the quiz as well. So we've got another turning point at minus 2 over 3. And negative 256 over 27. Are the rest of you getting that same horrible fraction? Yes, cool. Yes, you should be. All right, so that means one of the turning points is in the third quadrant. Okay, good. Well done. Okay. All right, so now let's just put it all together in the last couple of minutes that we've got. Remember our shape. It's first concave up and then it's concave down. Okay, let's just go back and look at everything again. Okay, y-intercept at 0 and negative 8. X-intercepts at 2 and -2. Turning points at -2/3 and this nasty -256/27, or at 2. So in other words, your graph is doing something like this matrix. Okay. Oh, what a horrible shape. My apologies. Really not very nice. Okay, so we know that it has one of its turning points on the x-axis. So there's our x-axis. Okay. So this point over here was 2 and 0. What was our other x-intercept? -2. All right. It has got a negative y-intercept. So it's something like that. There's the y-axis. So over here, that would be -2 and 0. This point over here would be 0. Hang on a second, that's not right. If that turning point is in the third quadrant, sorry, I'm just realized my mistake now. If that turning point is in the third quadrant, then, sorry, our y-axis would be somewhere over here. So that would be 0 and -8. That point over there is -2/3 and -256 over, what was it? 27. And then that would be -2 and 0 over there. Okay, and that's what our graph would end up looking like.